Okay, welcome everyone to today's live science. My idea is we're going to be doing science live on stream. And I think this is quite a cool, interesting concept because the idea is that a lot of these things happen behind the scenes and not in the public eye. So if this to be recorded on YouTube, so you can all see kind of like what thought processes go on inside the minds of researchers when they're actually discovering this stuff is quite cool. And potentially some of the aspiring researchers amongst you can get a feel for how it's done in real life. So yeah, today's theme is going to be on infrageometry. And this is a budding new field of study with Carlos leading the way on that for us. And really exciting stuff. So yeah, I think Carlos is going to do a lot of presenting. We might have one or two fellows join in during the live science session today. And yeah, with that, I'll hand it over to Carlos, and he's going to draw some pretty pictures for us.
Indeed. Well, thanks very much. Thanks very much, James. Sure, we are resuming our work on infrageometry. For those of you who followed the Institute's activity in the last few months, you might remember that we started off a few months back with Uti and Jonathan, and since they've both moved on, and but the progress on the project needs to continue. So we found some time to finally get back into it, and I am excited to be here to give some of the basic definitions, make sure that everyone is on the same page. Nick will be joining later, update James with a lot of the sort of more detailed side of the project. And nonetheless, tackling one of the long-standing questions that was unresolved back when we started the project and still unresolved today. Stephen and I had a conversation about it. We are still working on it, which is the definition of functions. It's one of the most elementary things that one needs to think of in terms of functions in the sense of scalar fields on our spaces. But we will get there. I think we have quite a lot of promising initial definitions that seem to be very natural and are a bit more refined than what we had at the beginning of the project. Our initial ideas were very naive and very sort of early stages. But now I think we have quite a firm ground to build on. So for doing that, I'm going to share first briefly the whiteboard just to give you a sense of. Actually, the pictures are good enough in our packet currently, so I can just share the notebook, and I'll use the whiteboard for brainstorming and discussion afterwards.
Cool. Can I ask some questions as we proceed?
Yeah.
So I would like to know the motivations with this approach. So I guess there's many different ways of tackling this concept of an infrageometry. What's the motivation to get to functions as the first thing?
Functions we are not going to get to as the first thing. Let me just hide this. This is super annoying. Yep. So we are going to cover essentially what differential geometry normally begins with, right? So there's an idea of a manifold, there's an idea of a sort of space, and on that space there are paths or submanifolds, and then there are functions, which are sort of features that you put on that space that you could think of as sections of some fiber bundle on top of the manifold, and so on. So the claim here, as I hope to communicate in the first sort of half of the session, is that the basic notion of manifold, or what we're calling the space graph, essentially, is, I think, now well motivated, and it's well founded by the fact that the notions of vector fields, vector bundles, curves, and so on are well defined, and they make sense in this context. And this is what I will show very, very intuitively in a moment. But when it gets to functions, this becomes trickier. And why do we need functions? Well, curves and functions are sort of the bread and butter of differential geometry, right? One could imagine that all of the tower of modern differential geometry is built, of course, on the notion of the real line, but and that's how you define your continuity of charts that are mapping into some Cartesian space or some Euclidean space, things like that. But the reason why we need functions so desperately is that that's what calculus is about. And I mean, geometry without functions, it was sort of like Greek geometry and sort of more classic Euclidean geometry, right? We need to infuse our spaces, our shapes, our geometric entities with some degree of calcularity, right? Some degree of feature space to begin to make progress in the way of what modern differential geometry has done. So that can be captured very simply in what is called the fundamental theorem of calculus. And of course, the fundamental theorem of calculus has a formulation that a lot of people might be familiar with, which is your high school derivations as the or integrals as the antiderivatives kind of result. But the fundamental theorem of calculus actually extends into manifold theory by the higher dimensional generalizations of that, which are generically called Stokes' theorem in sort of more generality. In 3D, these are the so-called Stokes' or Green's theorem, Gauss's theorem, and the potential theorem, or conservative function theorem, or whatever, which is the dimensionalities of points to one-dimensional to two-dimensional to three-dimensional. So these are collectively known as Stokes' theorem, but I like to call them just the fundamental theorem of calculus, because essentially that's what's happening thematically all along. This idea that having some information about the function at the ends of an interval can actually give you information about the behavior throughout the interior of that interval, right? This is the sort of the general notion of the fundamental theorem of calculus, that if you know the primitive or antiderivative of your function at the ends of an interval, that's the same as integrating the entire function throughout the interval, right? So there's this idea of boundary information determines bulk information, right? And there's this sort of equivalence between the two. So that's the general theme, the general idea of the fundamental theorem of calculus. Oh, I think Nick just joined us.
Yeah, hi guys.
Hello, Nick.
Hey, Nick.
Good to see you. So James just asked why do we need functions? I was just giving a very brief overview of the motivation of what we're doing here, and I said that following up from what we did before in our previous sessions, we have a pretty firm understanding that I will explain in a second to update everyone on what the space itself should look like, what curves, tangent spaces, tangent bundles, tangent vector fields, and so on should look like. But functions are not so obvious. And so James asked, why do we need functions in the first place? And my answer has been, to me, what differential geometry does is essentially is the context on which you can formulate the fundamental theorem of calculus. Almost, it's kind of you want to have the right mathematical framework where that theorem has meaningful expression. And so I was summarizing it as essentially, having boundary information is equivalent to some bulk information, right? Under some assumptions, under some constraints, that's essentially the statement of the theorem, the fundamental theorem of calculus. So, in very concrete terms, the fundamental theorem of calculus that I want to recover as a goal, hopefully in the immediate future within the project, is the one-dimensional or 0 to 1 dimensional, because really a fundamental theorem of calculus always is sort of connecting two dimensionalities. So the 0 to 1 dimensional 0 to 1 dimensional fundamental theorem, meaning the traditional one, but in the context of manifolds. So this is sometimes referred to as the conservative function theorem or the potential theorem, which is the idea that you can compute a line integral along a path to calculate the gradient difference, or basically the finite difference of a scalar field, right? This is the idea. By integrating the gradient along a path, you can get the difference of the value of a function on there. So if that were something like gravitational potential or something like that, or electric potential, those are the traditional sort of like work function by the interaction or the field or whatever. So that's the kind of result that I want to work towards. And I think we have the vector part covered. So what is a vector field? What is a curve? These things I hope are sufficiently clear and implemented, and I think we have a good understanding of them. However, what a function should be is not so obvious. So I'm gonna recap in, I hope not too long, maybe 10 minutes or so. I'm going to recap all the part that we think we understand fairly well, and then I'll pose what the problem is with the definition of functions. And it's not really a problem of an abstraction. It's more decision paralysis, that we have too many options and there's a little bit too little constraints at the moment that we have. Anyway, so unless James, you have another question more generally, I'll just get on.
Yeah, no, I'm keen to see how you do this.
Cool. Oh, hello, Dugan. Hello, Ellie. So just answering this question very briefly before I get on the explanation. Yes, so Udi might actually be joining us. He's very busy with exams, and Jonathan got busy with other endeavors in life. I mean, never discounting the possibility that there'll be future collaborations, but at the moment, the infrageometry, the weight of the infrageometry project rests on my shoulders and the people's shoulders here on the call. So I have my whiteboard ready. So when we get it to the point where I don't have more code, we can just move there, because I think I need to draw, I need to understand visually what we're doing. But before that, we have some nice code that is going to show us the basic concepts. So remember that the motivation for infrageometry is that we are motivated or we are somehow enticed by the Wolfram Physics project, that this idea that hypergraphs can be representing something like a space-time manifold. And so the idea is, okay, so we might be thinking that those hypergraphs kind of approximate in some limit, in some high vertex count limit, smooth manifolds, but we would want to maybe have a theory or a framework that treats those hypergraphs explicitly as spaces themselves. So we don't have to assume, large n limits or anything like that. We can actually treat the hypergraphs themselves, however small, as full spatial information. So the idea is very simple. So first of all, I can show you a little bit of how we can generate these hypergraphs, just to have something to work on. So I have this kind of hacky function that is just going to generate some nicely looking random hypergraph. So for example, this one. I could also generate some by rewrite rules, which is kind of what the Wolfram models do. For example, I could be having this every time I find a ternary link, I create a triangle of binary links. Every time I find a binary one, I create a ternary one, and in the process creating a new vertex. So if I take some simple initial hypergraph, you can apply the rules in different generations, and then you can get increasingly more complicated hypergraphs. So anyway, we also have a tool to draw in our Padlet, but this is just sort of to showcase a little bit. Okay, but so what is the main idea of infrageometry? I mean, you might be thinking the Wolfram Physics project already tells you hypergraphs are like space. We just need to understand how these evolve and are rewritten and so on. So what's new from our perspective in infrageometry? Well, what's new is this philosophy called edges as places. So the idea of edges as places is very simple. So imagine that we have this, and this is our spatial hypergraph, right? So we want to think of this not as some kind of approximation to continuous space, or some kind of early iteration of a process that's going to take us to a large n limit that will approximate or converge into something like a continuous manifold. But we want to think of this as our spatial information. This is finite, complete, total spatial information. So what that means is that so obviously vertices and edges have different roles because they are informationally distinct. Vertices are some set, maybe labeled, and the edges are just collections of those vertices, right? So really, it's just a set of subsets in some sense. That's undirected, simple for concreteness hypergraph right here. So the idea of edges as places is that we need to distinguish two kinds of places, and that's why I call them places and not vertices or edges or anything like that, or points or things like that. So a place on a spatial hypergraph is either a vertex or an edge, and obviously say a vertex place when it's a vertex and an edge place with an edge. And so how should we think about that? Well, here is a function that basically takes the edge places of a hypergraph and highlights them by adding a new vertex at the center of every edge, right? So that's one way to very clearly visualize these things. So how should you think about that? So the idea behind this edge place notion is that vertices are sort of the landmarks of a landscape, right? Like these are the points where you can sort of inhabit, right? And edges are the betweenness information between those places, right? So these are places that you can travel through, but not places where you can reside, right? So imagine these as somehow like checkpoints in a desert or something like that. I mean, or stations in space or something like that, right? It's edges and vertices have these two different things. So an edge is empty space between the outposts that you can visit with your spaceship or something, right? So that's kind of the idea that you need to keep in mind, because it's going to be useful for the definition that will come in a little bit. Is that clear, James? Are there any questions, clarifications?
No, I like it. Yeah, makes sense.
Yeah, it's very simple. It's just I want to make sure that this is a clear concept. So yeah, keep in mind vertices, outposts, edges, space in between that we travel through. Okay, so if you give me a spatial hypergraph like this one, I can just empty all the edges, and what I get back is this labeled two-kind bipartite graph that, two typed graph with vertex places and edge places. So in this particular picture, the black dots and the red dots. Okay, so what's the idea for a path in this space? So the whole first initial motivation, again, building towards these sort of dual constructions of functions and vectors. The first, or functions and curves. Let's look at curves first. So what is a curve? Well, a curve is basically a trajectory of places that you can visit. Now, because I'm saying that the vertex places are the ones that you can actually inhabit, my definition of a path, more specifically, is going to be a sequence of vertex places that are connected by edge places. So maybe actually this is where my Blackboard is going to be much more useful, because I have the tangent visualizations here, but let me just unshare very briefly here, and I'll share on my tablet, because I think it's a much more helpful picture here. Hope everyone can see this. So
yeah, I can see.
Yeah, so just what I was saying, but now in drawing, you begin with a spatial hypergraph. You take the vertex places in black, you now take the edge places in blue, and effectively what you have is a connectivity pattern that is what we would call more technically the incidence pattern of your hypergraph. Now note how each, so for example, this was a good example, this one. This edge over here becomes this edge place in blue, and the incidence pattern, meaning the fact that this edge is incident on these three vertices, becomes the existence of these three undirected edges, right? So that's kind of the essence of this edges as places philosophy. So what is a path? Well, a path is going to be, so let me use a different color, maybe something like some dark red or something. So a path is going to be something that, make it bigger for everyone's benefit. So imagine that we are, standing here with our spaceship, whatever, and we want to go to some other outpost, right? So if we have the hypergraph above, what that's telling us, imagine I have my spaceship here, and I want to go somewhere else. Well, if I'm here, basically this tells me that there's empty space connected to these other outposts. This, maybe this is called Q, and this is called R, and this is called S, just to give some names, right? So the idea is, if I'm in Q and want to travel to P, I need to go through the edge that is connecting P, Q, and R in this particular case. So instead of just abstractly saying that on top of a hypergraph, the construction of the edge places graph, the one in the bottom, is that all you do is to take a more conventional path in the sense that I travel first to the blue vertex, and then from the blue vertex I can either go to P or to R. So if I wanted to go to P, I will go to P and do that, right? So if I want to reach, maybe let's call this whatever, T. If I want to reach T, then now I can say, well, I can just follow on the same path, reach the edge place of that ternary edge, and then follow all the way here. Okay, so what if I wanted to go to Q, from different paths? So let's draw a different spaceship, maybe a green one. So this one is more like that. What if this spaceship wanted to go from this edge? We can go O to, for example, S that we're calling here. This is R and this is T, right? What if I wanted to go there? Well, what you can do is obviously first travel through the single edge that exists here. Okay, go to the edge place, then connect the edge place with P. There's unique. But now if I want to go to S, I actually have a choice here because there are 3 edge places that connect P and R. So those would be 3 different paths that the green spaceship can take in its way towards S. So it could go through that edge place, it could go through this edge place, or it could go through this edge place. And then here again it will be unique because that's how you get there. So generally speaking, that's the notion of paths.
Or do you have like, why do the blue edges connected to each other? It's a bipartite graph, right? I think that you have like a
that's a mistake. That's a mistake. Sorry. That's a mistake. That's a mistake. Yep. Thanks, Nick. This is a mistake. There is no disconnection. Sorry. This connection is here.
Yeah.
Sorry. yeah.
Glitch in the matrix.
Yes. Sorry. Thanks for pointing out. Apologies. The previous diagram was also mistaken for that. But sorry. I hope it makes sense now, right? All right. Yeah. So anyway, so these are the notion of paths, and so a general definition of a path, P, we can call is a sequence of vertices through edge, to vertex, through edge, to vertex, through edge, etc. So the general pattern is going to look something like that. Black dots intermediated by blue dots or red dots if we go back to the code, right? Right. So that's the notion of a path. Okay. In some sense, computationally, we are not doing anything other than just defining paths on a bipartite graph that has some constraints on how we can connect things. So, for example, we are constraining that our initial and final points are black vertices, and we are constraining that you can't basically go from an edge to itself. So there are no loops on the edge places, if you will, right? But other than that, we have general paths on this edge place graph, and that characterizes what the possible curves or possible ways to navigate your space look like, right? And if you yeah.
Oh,
Please.
sorry, you just made a statement. I just wanted to maybe iterate on a couple of ways to confirm the statement of no edge places can loop to themselves. So in the case of 2 edge places perfectly overlapping, what would happen there?
Can you repeat again? Yeah.
So just like if you were to put an additional hyper edge in the bottom right corner that perfectly connects ST and that bottom right dot. So if there's 2 hyper edges that connect the same vertices, then it would be an edge place that kind of exists in the same space.
You mean if there was a second edge of the same kind here?
A multi-edge.
A multi-edge.
Yeah.
Right. So just to point out that I did say in the beginning that we are thinking of simple hypergraphs for simplicity.
Okay.
Pun intended. But the point stands. We don't have to. There's no real. It's not a problem to take multi-edges. In that case, you would find something like that, right? You will have some not like here, sorry, but something like that, and it will turn into something blue like that, right? So you will just have that, and this is not connected here, right? Like this is just a different edge altogether that is not connected to the other one. This is bad implication of the drawing. So this one goes here, and this one goes here, right? They are not connected. It's a good question because it allows to visualize what we're meaning here. It's good. Okay. There's a question here by Dugan. Can we say a path is an embedding of a canonical path on a finite? Judy was terrible putting the emoji thing. On a finite linear. Is that the word? Linear. Linear graph into the hypergraph. If we made that notion precise, then that could be a definition. The problem is that what it means to be an embedding is it's up for definition, and that's exactly why we use this edge place construction. It's simply a way to because we're interested. The edge place construction is very, very much motivated by the notion of path, because if you take seriously the statement that your edges give you the in-betweenness of places, of landmarks, then if you say that there is these edges between these vertices, those are essentially capturing what paths can be taken between them, right? But because paths are these source target kind of constrained things, we don't necessarily want to assign to a space, right? Space is not made of paths. Space is made of space, right? Paths is how we traverse space. So that's why we begin with a hypergraph that is simple, undirected, and then we parse it in this sort of path-like manner to get what is effectively just a graph, right? Like you could, the graph here that I will show us something what we define as the tangent bundle more specifically, but even this undirected simple graph where you're essentially defining what some people might call the line hypergraph or the line graph of your hypergraph, or the incidence graph of your hypergraph. That's essentially the trick to define paths in a systematic way, right? So I don't know, Dugan, if that answers your question. Let me see, Lyubov. Actually, it is more the other way around, because you need to do this disambiguation of possible embeddings from hypergraphs to graphs. Yeah, that's right, Lyubov. Yeah, thanks for the clarification. That's kind of where I was trying to say here. Okay, so with that definition out of the way, that's a very important definition. That's something that, it looks very harmless and trivial, but this is taken some time to mature and to confirm that this is hopefully the right definition. Then the concepts of differential geometry, of sort of tangential structure in manifolds naturally pop up. And for that, I'll go back to my notebook to show you the active, computationally active stuff. Right, so if we have a notion of a path, remember how in differential geometry we define tangent vectors. We define tangent vectors as infinitesimal paths in some sense, right? We define tangent vectors as the way we are pointing when we are standing at a particular location and we have a curve or path going through that location. A tangent vector is effectively the instantaneous velocity that we have following in that path. So with that idea, in the current definition of a path, it's fairly obvious that our definition of tangent vector should essentially amount to a directed edge from a vertex place to an edge place, right? So the graph, the undirected graph that I had before, which was essentially an incidence graph or a line graph defined from the hypergraph, now becomes this, now has direction because vectors are directed and we need to distinguish which way we're going. So to visualize this, I have this little manipulate. Hopefully it runs.
So it's not other way around, right? Not from edge to the vertex.
Aha. It can be from edge to vertex, but that's the definition of negative. So I'll get there in a second. Why is this not running? This is...
You need to next cell. Next cell actually runs it. This is just
Yeah, that's right. Sorry. Okay, so remember we have this spatial hypergraph, simple connected, not necessarily connected, simple undirected hypergraph. We find our edge places. We have this aggregate set of places now that are distinguished, vertices or edges. And so the tangent spaces at each point, and I'm going to be precise, the positive tangent spaces, just to Nick's point, are the directed edges from vertices to edges. So if I move around this slider, which basically goes around the different vertex places, you will see the different, for example, tangent space over there is just pointing out to all the nearby edges. If I move, that's a different tangent space there. That's a nice looking sort of, 6 element or 5 element tangent space. Each position has its own. Due to some technicalities of the hypergraph backlit, I couldn't render the hypergraph in the background at the same time, but we will fix this, I'm sure, very easily. It might be my ignorance of how to make it work, not the fact that backlit is limited. Anyway, so if we take all these constructions at each vertex, we kind of approach our neighborhood in the nearby in the adjacent edges. Then we have the collective tangent bundle by just putting all together. So this is the usual definition of tangent bundle. As I say, more precisely the positive tangent bundle, because these are the edges that are outgoing from a vector space. And it's very important to understand that positive and negative, vectors cannot be positive or negative, right? I think this is something that it's easy to forget, but vectors cannot be positive or negative. They just, when you have a vector, you know what its minus is, but there's no such thing as a positive or negative. So just because we are doing this pairwise sort of bipartite definition of the edge place graph, we now have a notion of what is positive, what is negative in a more artificial sense. But it doesn't really matter. It just means that every time you have one notion, you have the reverse notion by taking the contrary direction. So the full tangent bundle, in some sense, is the sort of symmetric bidirectional graph that basically joins all the bipartite graph from vertex places to edges, right? Okay, questions, technicalities. It's very simple.
Yeah, it's very nice. It's very elegant. I like it.
Yeah. So just to make a comment at this point, so this was, again, it is very trivial. There's nothing sophisticated going on here, but it does require this second layer of consideration. And the intuition that I have, I don't know if this will prove to be correct in the end, but the intuition that I have is that because in continuous geometry, all points are equal, right? Like there's the points are actually in a completely egalitarian state. They all live, they're all points of space, parts of your manifold, whatever, points in your topological space or whatever. If you look at your edge place graph, or the tangent graph, or I'm calling here the tangent graph, this looks just like a graph. The one I drew, or this one here, this is just a graph. But the vertices now have two different natures, right? And so you might be thinking, okay, so does that mean that my manifold is going to have two different kinds of vertices, two different kinds of points? And my intuition is that no, because in the continuous case, you have the continuity structure or the differentiable structure with whatever instantiation you prefer. Abstract topology, topos theory, just a good old differential geometry with coordinates, atlases with the differentiable charts onto some abstract metric space. It doesn't matter how you do it, but you have this notion that allows you to define differentiability, continuity, differentiability, and all these notions, right? The fact that you are in a topological space, blah blah blah. We don't have that here, right? I mean, we could try and pretend that we do, and we just do it like discrete topology, but that's not good thing, because I mean that's sort of dishonest to the point of what topology should be doing, or differential topology should be doing. But what we can do here is this notion of infinitesimal, what it means to be infinitesimal or approximately close and so on, which is what all this continuity structure is good for. What we do it here is we just discretely implement it, right? So we say that this point here, in the upper end of the graph is not infinitesimally close to this other point here, because they are just two different points. They are a finite distance apart. But this point is infinitesimally close to the edge place on which it is adjacent, right? Because that's sort of the abstraction. As soon as you move away from this point, you're already in the interstitial space between actual points or vertex places, right? So that's how this is just a comment. This is not sort of some technical point, but this is just my interpretation of this right now, is that the reason why I have expectations on infrageometry working out, or at least higher expectations than I did before, is that we've given this extra structure on top of just a plain hypergraph. We're giving it this sort of edge place construction, which is very, very pedestrian, very simple, but it has enough, I think, granularity and enough structure that it might well capture what the continuity structure, the smoothness structure does in the continuous geometry. So anyway, that's just as a comment, as a sort of a point of intuition that people might agree or disagree with. So what's a vector field? I mean, now things should follow more or less in a straightforward manner. I think something got, I think because I was using hypergraph unit, Nick, I think the embedding was not working well, because I mean, obviously you can see that it's sort of clamping up all the vertices, and that was the problem I had, by the way, why I couldn't render the other things. But anyway, what's a vector field is, I mean, we don't need to look at this now, obviously. What a vector field is you assign to each actual place of your manifold not to each actual place, but to every place of your manifold, a tangent vector, right? So naturally, when you assign a tangent vector to a vertex place, that's always going to be a positive vector, because that's always going to be from vertex to edge, right? And when you assign a vector to an edge place, meaning from red to black, that's always going to be a negative vector. Remember, positive and negative here is just a label. Don't fret that we are making some actual distinction between positive vectors and negative vectors. It's just an artifice of the fact that we have a bipartite graph, and therefore, when you want to assign a distribution of edges on this bipartite graph, you're gonna have to contend with that. And I mean, why? Not all distributions of vectors are going to be a vector field. This is very important. So, how should we define a vector field? A vector field should be defined in such a way that you can answer the question, give me a vector field, can I find integral curves of this vector field? So for that, I will probably have to use my tablet again. So I'll quickly switch to draw some stuff, because this is much easier to just draw quickly. And hopefully everyone will agree on my proposal for a definition of a vector field. Let me put the tablet in writing mode. Right, so we all agree that tangent space or positive tangent space at a vertex P looks like that. Forget about functions for a moment. And let's consider, okay, so what should be a vector field here? Maybe that graph is too crowded. So let's draw a new special graph, maybe something that looks like that. Maybe one here. something like that. Okay, let me label with numbers. It's just easy. 1, 2, 3, 4, 5. Okay, so if I do the edge place construction, so I'm just going to highlight the edge places in blue like that. A vector field, which I might want to label like that, let me call it V, capital V, okay. It's going to be an assignment of the form, give me any vertex in the edge place graph, and I'll give you a directed edge, right? So that means, okay, so maybe it's useful to clone. I should be able to just copy this thing. Can I?
I think when you copy it, you can drag it off that same spot. So select it, copy, and then just click and drag.
Okay. Nope.
Oh.
I think it's another option here. Duplicate. There you go. There. So, okay, so if I have the graph and I want to simply define a vector field there, what I'm going to do is I'm going to delete the actual edges surgically. Let me see if I can do it properly. Okay. Okay, almost. So I have this graph. And now it's bare, but the point is these can be connected, right? So maybe I'm going to do it dashed. Right. I hope everyone agrees that that's the edge place graph that we get from that hypergraph. And so a vector field V will be an assignment of give me any of these vertices and I'll give you a directed edge on that edge. So for example, it could be something that looks like that. In here it's going to look 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 like that. In here is going to look like that. In here is going to look like that, for example. In here is going to look like that. In here is going to look like that. And in here is going to look like that. Okay? So what you need to make sure is that there is one tail per vertex. Exactly one tail per vertex. That's the important thing. Everything else is allowed. And still keeping simplicity in the general sense. Okay. So that's a valid vector field on this space. And so the question of what is an integral curve of this vector field should follow exactly the notion of integration in traditional differential geometry. So let me very briefly remind you of that notion. You know that when you have some manifold M and you have some chart, well, not some chart, but some open set, some region where you have a vector field defined, V, you know that effectively what you're doing is assigning tangent elements at every point of your space. So when you actually take a chart on this open set, that becomes, so you turn this into something in Rm. What that becomes over here is an ODE. So an ODE basically meaning that you have something that looks like this. Some function of x. That's what it turns into. So it's an ordinary differential equation, and therefore when you integrate it, given enough regularity conditions, you're going to find solutions which are curves. So these, when you pull back to your manifold, they are going to be curves that are tangent to the vectors at every point. Right? That's the property of an integral curve. That's what I mean by integral. Integral curve means that your tangent vectors coincide exactly with the values of the vector field as you flow. Okay, so keep that sentence, put a pin on it, because that's exactly how we are defining integration in the infrageometric setting. All we are saying is that if I want to have a path, maybe I do this orange. So if I want to do an integral curve C, the curve will have to follow a path so that the vector is tangent to the curve all the time. So an example of an integral curve is, for example, to go from 1 to 2. Right? That's an integral curve. Why? Because that path is made precisely of the edges 1 to this edge and that edge to 2. Right? So that's an integral curve. But we can find other integral curves. For example, I can go all the way from 1 to 3 as well, because I can see these two edges are pointing there. So this is, for example, we can call this C1, but we can also go like that, right? And I can call this C2. Remember, each of this C1, C2 is a sequence of vertex, edge, in this manner that we said earlier, like this general pattern that I have up here, right? So I'm just simplifying. But there, there are other integral curves, like for example, I can, so I cannot go, we're not taking edge places as starting points, so I would never ask for that. So if I start from 3, I could go from 3 to 3 in this way. This is a C4. I could also go from 3 to 2, according to this diagram, yes, I could go from 3 to 2 and then back again. This is a C5, right? And then down here, I could do, 5 to 4 for sure. This goes like that. So this is a C6, and that's it, because this curve is going here and it's sort of dying there, so I can't really integrate anything there. So this is in some sense the fully integrated vector field, right? All these curves. So in my opinion, this is why this edge place construction makes sense, because it gives me an immediate tool to define what integrability of vector field is, and that is kind of almost the one half of one of the 3 legs of the tripod of differential geometry, where one is sort of differential topology, the other is linear algebra and higher algebra and commutative algebra, and the other is analysis, measure theory, and all that stuff, right? So one of the 3 golden legs of the stool of differential geometry is this idea of integrating manifolds and the tangent structure and so on. In my opinion, this is appearing as very promising just at the level of the data structure, right? Because I haven't done anything. I haven't done any. I didn't have to compute anything. It was just definitionally obvious what integrating a vector field would mean in this context. So. So this is more or less the story of the tangent structure. I could leave one of the open questions maybe here on the screen for a later discussion before I move on to functions, which how do I want to, maybe some aggressive red. Open question. What is a short way to write it down? What is the algebra of vector fields? So, for everyone to have a reference what I'm referring to, part of the very nice story of differential geometry on continuous manifolds, on smooth manifolds, is the fact that once you define the tangent structure, curves with tangent vectors and vector fields and so on, a very neat result is that the set of all vector fields, using your favorite notation, or some people call it vect M, so I think that's the most explicit, I'll use it here. This signifies all the vector fields fields on M. Let me collapse this. And what's cool in algebra, the algebraic perspective of differential geometry, is that there are natural operations on that space. So vect M has a structure of what's called a finitely generated module, but that's just a bit of technical. But what it means is that you can add vector fields, that you can multiply vector fields by constants, by functions more generally, but we're not talking about functions, so that's kind of forbidden for now. And most importantly, you can take Lie bracket of vector fields, or sometimes called the commutator as well. By the way, the commutator effectively, this Lie bracket, if you try to see the proofs of how it is defined, so it might get a bit dizzy because it's a little bit of more advanced differential geometry. Oops. What happened?
Was it the tablet?
Is it? I think. No, it should be fine now. Yeah. So I don't know why it unmuted itself. I didn't touch anything. I don't know. It's doing crazy things. Oh, is it here?
You sound better now. Should be fine.
Okay, I could have done it from here. Okay, fine. The Lie bracket of vector fields is quite a simple. Conceptually, you can understand what it comes from quite simply. Remember how a vector field is this idea of a flow that when you express it in a local chart, it basically amounts to a flow that you resolve as an ODE, ordinary differential equation. So you have this time parameter is effectively, t equals 0 means everything is fixed, and as you run t to some positive value, sort of your manifold starts to flow, right? In that area, according to the field. The commutator, the Lie bracket of vector fields, effectively amounts to computing the difference of paths if you take first one flow, then the other, or first the other, and then the first, right? So if you have two vector fields in some region, so just to make a quick conceptual summary of what this means, if you have, maybe this is not very wise to just use this color here. So as a very quick conceptual summary here, you have some manifold, you have a vector field maybe in red here, I want green, that has a flow represented by this integral curves, right? They're flowing maybe in this direction, right? And I have another vector field with integral curves that flow in this direction, for example, right? The commutator bracket, the Lie bracket, effectively is measuring something like this. So it's asking, okay, if you start in that location, and let me call this x, and let me call this y, right? So the commutator is saying, if you go first with x, following this way, first with y, and then with x, I end up in this position. If I first flow with x, and then with y, I might end up in this position, right? So depending on how these vector fields are, right, those 2 points might not be, this might be some finite delta, right? Like they might not be like the same position. So that difference over there is measured by the bracket xy. So this is y and this is x. So delta, again, very schematically, is roughly that idea. Oh, hey, Uti, welcome. We're just doing recap, so you're perfectly in time for the end of the recap, effectively. Right. So that's why we like it, because it's a Lie algebra. It's something that's very well studied. All of modern physics, or most of modern physics, has been built on Lie algebras and all these concepts. So this is a Lie bracket, and so it's very powerful, and it's I based all my PhD around this idea that you have a Lie algebra and you do things with it and so on. And so the question here is, what is the analog of that kind of structure in this context of infrageometry, of discrete embodiments of vector fields? So we are happy because we have a nice notion of positions, places in space, then betweenness relations or betweenness information between the positions, and then we have a nice notion of curve. We have a nice notion of what it means to be infinitesimally away or close to all these points. This turns into the notion of a vector field giving you an integral curve. These things are sort of nice nicely stacking up on top of each other. But then we are a bit taken aback when we are asked, okay, fine, but where is my Lie algebra of vector fields here? Like how do I see the algebraic aspect of all these things? Which, if we're claiming that we can seriously take hypergraphs as the discrete analog of manifolds, taking this perspective, then we should be able to have something like the commutative algebras and the modules, Lie algebras, and so on that differential geometry is usually presenting. So that's an open question. I have my thoughts. We can leave it for a bit later for open discussion, what we think would be a way to recover these kinds of things. And by the way, the open question is not the Lie bracket. The Lie bracket will be sort of the cherry on top. But the open question really is about every single algebraic structure on the smooth case, right? Like the fact that you can add vector fields together, the fact that you can, and for that matter, the linear structure of the tangent space. I mean, we don't need to go to all the way to fields, but just at every point in classic differential geometry, we in the classical setting we have the points so the tangent spaces at every point are vector spaces. This is something that it pops up out of your construction. It's not by definition. I mean, it's almost by definition, but it's not exactly by definition. So in our setting, where did that linear structure go? I mean, clearly we have a finite set, so we cannot have a literal vector space. Although you would see some people in the literature that roughly treats this problem, just saying, okay, you have 5 element generated vector space over R or over Q or whatever. I think that's very lazy. It works for some things, but clearly doesn't resonate with the flavor of what we're doing here, which we're trying to be very minimalistic and very proper to the finite and discrete, finite, generative, if anything, setting. But we don't want to just like take something that is given and just run with it by finitely generating vector spaces at every point of your graph. Okay, is the question clear, at least to everyone here?
There was one question in the chat about what happens if there's a fork in the road. In other words, if you can take two different paths, how does that translate to the vector field?
Okay, so yes, let's let me see the question here. Hold on, how is the vector field integrated when a vector from a vertex points into a hyperedge containing 3 vertices? Well, the point is, okay, maybe. So note, Dugan, note that I don't know if that was answered already through my explanation, but note that every time. So once you translate what I'm calling the edge place graph, so basically this blue dots, you stop having any ambiguity about edges because all you have is a bipartite pairwise graph. Standard graph. So that ambiguity disappears. But the other question might be relevant here. One is when there is a fork in the road, basically. Yeah. So there is a fork in the road here, right? In this diagram. I'm a bit scared of deleting this thing, so it might make it a bit clearer. So there is a fork over there, right? Like this this edge over here makes the vertices, makes the blue vertex over here, right? So there's no problem. We just treat it as another vertex. There's no ambiguity. Like once
how does that translate to the vector field diagram? Maybe that's actually even my question. So what would that look like on a vector field diagram?
What do you mean a vector field diagram? You mean
this chart, this ODE.
But this is it's important that this is the analogy to the continuous case. I'm not saying that this is representing what we are doing. It's the other way around, in fact. I mean, this is a well-known case, it's the smooth case where, you have an ODE, you have a flow, so you can compose flows, you can define infinitesimal flows, you can define the bracket, all these kinds of things. We can do that. We can define something like a discrete flow if we want to go there, which we might, but initially, in this very minimalistic definition of integration, all you care about is the fact that if you have points, if you have vertices, you can go through them. the constraint is how you place your initial and your final point, but other than that, there's no constraint, right? I mean, and technically there is the constraint that you can, your path has to be of this form, right? So you can't come back from like the minimal length path is of the form black, blue, black, right? So for example, in this case, when I am in this situation over here, and I'm looking, for example, I mean, it could be anything. Like I could be in the beginning here. An integral curve here is to go from 1 to 2, right? But I want to explicitly maybe write down the ones that are not allowed, and maybe that will clarify. So in purple, I will write the ones that are not allowed. So this is not an integral curve, for example, right? One that goes from 1 and goes back to 1. That's not an integral curve. That's an integral curve here. C4 was highlighted as one going from 3 to 3, right? Because I had drawn an arrow from 3 to the middle edge here, and then another arrow from the middle edge back to 3. So that's why I can do a round trip on 3. But I cannot do a round trip on 1. Can I do a round trip on 2? Yes, I can do a round trip on 2 by going to the middle edge in the same way, right? So that's allowed. But for example, doing a round trip on 4 is not allowed. Doing a round trip on 5 is not allowed, right? So these are not integral curves. And so, for example, it's not an integral curve to go from 1 to 5 either, right? Because I get to the middle edge, and then there's no value of the vector field that is pointing from the middle edge into the vertex again, right? So yeah.
So are you essentially covering those vectors with the curves? Right?
Say it again. Say again.
You're essentially covering them, right? So you're not allowed to intersect a bunch of curves with the same vector, right? They're not allowed to have the common vector.
Okay, that's a very good point. So that's okay. So we can distinguish it. That's a good point. So just to distinguish that, there's one thing which is the definition of an integral curve, and then there's the flow, right? The flow is the family, sort of cohesive family of all integral curves in the smooth analogy. In our case, we might want to. I mean, this might not be easily distinguished or cleanly distinguished, but we might want to say that any such curve is an integral curve, but the flow is a choice of integral curves such that it's covering the vector field, is not intersecting, right? That might be very well. This is a very good point. So these are integral curves. And then a collection of such C's is flow when C1 intersects C2 is empty. Something like that. Just as a reminder that we are indeed separating the notion of an integral curve and the notion of a flow. It's a fantastic point, Nick. Thanks. Okay, any more questions about integral curves? I don't know, Dugan, if you're still in chat, if that resolved your question. I hope it did. But it's a very important point to clarify that, what's happening when you get to a fork, where are you going? Well, that's exactly why you need values on the edges as well. Okay, Dugan says, integrating a tangent vector field usually means start an initial vertex and a tangent vector rooted at that vertex and end up at some other vertex after some discrete time step. Exactly. So that's integrating in the original historical sense, so almost in the kind of first definition of an integral, right? So that's what we're doing here, right? Like you're saying, you begin at a point. If you have a tangent, vector, then you flow it, and it's almost like stepwise integration, right? I begin at 1. We can speak of it in that sense, right? I begin at 1, and I have one vector value at that point, so I just follow it. And then I end up in the edge place blue. So I have another vector there, I just follow it. Okay, I got to 2. So I could stop there, that's already a valid curve. Another curve will be if I start at 2 and I take this first vector here, then I'm gonna go to this place in blue. And if I only had the one back, then it will be only one integral curve going through there, right? So what the ambiguity, I think I understand Dugan's question here in the sense that starting from a point with a single tangent vector, with an initial tangent vector, might give you non-unique destinations. I think that's what we are getting at, right? But it seems here we are studying at the vertex and the tangent vector points towards the interior of an edge. That's in place. There's 2 time steps to traverse over to the next. Yeah, it does take 2 time steps, so to speak. We might want to think about the fact that we are taking an even number of steps. Right, Dugan, yes. So for hyper edges, the destination is not a unique choice. And yeah, that's an interesting point. That's an interesting observation. In my view, because we are also simplifying that we have single edges, right? So we are simplifying that, so that we have simple hypergraphs. So we have single edges on each pair or in each collection of vertices. It might well be that if you have 2 vertices, something like that, and you have 2 edges, so that there are 2 edge places between them. Like technically, with our current definition of vector field, a vector field would look like something like this, right? I'll have to assign a tangent here, I'll have to assign a tangent over there, and then I'll have to assign some other tangent here, and then I'll have to assign some other tangent here. So a vector field on this very small spatial graph will look like something like that. And so the integral curves of that will have, it will not be obvious where you're calling an integral curve unless you know exactly the names of your edges, right? So this will be one integral curve over here, and this one here will be an integral curve, right? But you can't go. So if I call the edge places, I give them some name. I call this A and this B, and I call the vertices 1 and 2, right? The path 1A2 is an integral curve, and the path 2B2 is an integral curve, but the path 1B2 is not an integral curve, right? So this one is, this one is, this one isn't, right? So this is an ambiguity that doesn't exist, and it's a very good question, because it's an ambiguity that does not exist in the traditional setting, continuous and everything, right? So of course there's some price to pay, and there's some ambiguity that you buy you buy concision and uniqueness by imposing structure, and because we have very little structure, we're gonna end up with some ambiguities. Any other questions? I'm just gonna turn on the lights.
Yeah, I just want to check in with Uti and see what he has to say about where we are at this point.
Yeah.
So hi. First, can you guys hear me? Because I've been facing from my microphone.
Yeah.
Okay. Nice. So so it's been a while since I've done the infrageometry stuff. Particularly, I think it's been 3 months, because last year I was full-time employed at Wilcom, but now I had I'm going through a semester right now, and I have my final exam tomorrow. So it's been a while since I've been looking at infrageometry, but yes, it was a pretty exciting project. Infrageometry's kind of been on the back burner for me. So I don't know. Sometimes it's just an idea comes to my head, but I don't have time to follow up. But yes, certainly I don't exactly know what you guys explicitly talked about, except the stuff let's just talk about, which is pretty interesting. A few updates on my side is that I was thinking about, I think that the discrete vector field idea that we come up with, the thing that I mainly worked on in the infrageometry side, like discrete difference operators between discrete difference operators on functions defined on the graph. I think there's a lot of deep mathematics over there. Turns out, and I was able to like relate it to like more algebraic concepts. Like I think it turned out to be the end, which I didn't really get to demonstrate. Turned out to be related to an idea about localization in rings. The main idea being that if you have a function defined in 2 points, then you can define the discrete difference as just the function defined on that point minus the function defined on this point. And I think Carlos might have said something about that in the review.
I did mention it very briefly, yes.
Yes. And then what you do is you divide it by the length or like the number that you assign that edge, which is supposed to represent like the discrete difference. And the idea is that when you're dividing by that number, you're explicitly thinking of that number as something which has an inverse, right? Like you're dividing it by, let's say, epsilon. So epsilon is an element which has an inverse, which is 1 over epsilon. And so technically you're just multiplying the difference in the length of the function, like the f of x minus f of x2 minus f of x1 multiplied by 1 over epsilon. Epsilon is like a unit in your whatever algebra. So you're kind of localizing at epsilon. You're making epsilon a unit. And so I remember there was this one discussion with Jonathan was also there, where we tried to basically figure out the algebra of like this function field, or like this function ring that we were defining in the graph, where you're allowed to divide by the length of the vector.
Yeah, and
yeah, right.
We're gonna get into that. Yeah. We're gonna get into that, Udi. Maybe we can continue the discussion of what you did when because we were just sort of priming the vector part, the tangent structure part, although we took considerably longer. But yeah, so anyway, so I think that's a good place to sort of put a bookmark and essentially move the page.
I was rambling a little bit.
No. It's just that we have a very important question. So what Udi was mentioning is so what he worked on is exactly the question that's on the screen right now. So this was the open question back then. I mean, it was very quick for us to realize that this was going to be an open question. So we hired Udi as a temporary fellow to work on this question, and he made very good progress. The idea of finite difference operators and so on, where you're replacing the notion that a derivative normally is an infinitesimal sort of instantaneous rate of change, and instead we were computing finite rate of change, right? So basically doing your calculus without taking the limit, kind of thing. And so a big push of that was to do with precisely this structure that I was referring to, the commutator bracket or the Lie bracket, and trying to come up with some alternative of a Lie bracket. I mean, unfortunately, we couldn't really find it. And in my opinion, one of the reasons why we couldn't really find a concrete answer to this question is the other open question that I wanted to talk about today, which is the notion of a function, right? So this is what I advertised at the very beginning that we were going to get stuck on. So just as a very quick definition, so everyone is on the same page here, functions, or as physicists will call them, scalar fields, are simply, in conventional differential geometry, you would have something like a manifold M, and you would have, the real line, whatever in your favorite interpretation, just floating there in your Platonic space or something. And so functions will be just assignments of M to R, right? So function will just be a mapping from M to the real line. So in some sense, these are sort of feature characteristics, feature distributions of your space. It's almost like, your manifold is your space in black and white, and then you put the functions on top of it is sort of this technicolor, and suddenly you can see, with all the rich details. So in some sense, we have an obvious definition of a function here, right? Like you say, well, if you have a set of places, then a function in the infrageometry sense. Maybe we can call everything infra whatever. So an infra function would be a function from the places to some scalar field. Here's where the name's gonna get tricky. Some algebraic field of scalars. It's tricky because obviously scalar fields. That's why I like to call them functions to keep separate the notion. So a field in the sense of an algebraic field of numbers, right? Like the complex numbers or the rational numbers or the real numbers or the integers and things like that. So I'm gonna, yeah. So basically we have something that looks like places. Vertex, edge places, not so important at this point. And we send them over to some field of numbers. So this is some, think of it numbers. So there's two legs to the question about the definition of functions. First, this one, question 1. How? Question 2. Which? Oops. Right? So these are the main two questions. This is how I summarize the problem of defining functions right now. First, the how. Let's assume that we all agree that there is some field of numbers. Let's say the real numbers, because we want to be very fancy and very advanced. And we already have, we cheat already and we invent, pull the real numbers out of our mathematical toolbox, and we say, okay, we have the real numbers. Okay, we have the real numbers. Fine. If I give you a spatial hypergraph, whatever, something that looks like this. Whatever, right? Some spatial hypergraph. How do we assign, and we know that this is going to be our analog for, what we are calling M, and we're going to have some abstract real line floating over here, and we're going to assign some function to it. I'm just copying the diagram, right? Just complete analogy. So how exactly? Well, for sure, we're going to have vertices being assigned real values. So f of a vertex, that should be a real number. Sure. But if we are saying that things exist in between between vertices, and the edge places have some entity where you can sort of walk through in between outposts in your spaceship or something, then we should probably also assign values to edges, right? In some way, because they are part of our space. It's just, it's just space that we travel through, not space that where we stay, but space nonetheless. So then the question is, how do you make this assignment so that your function has some kind of continuity property? Like obviously continuity really is a property of smooth manifolds, continuous manifolds, topological spaces, and so on. And we are explicitly, by construction, we're explicitly rejecting that narrative. We're saying we're going to try to get as far as possible without inventing a topology and just pulling all the machinery from topological spaces and differential geometry and so on, just automatically. We're trying to stay as lean as possible, as discrete, computational, finite as possible. And therefore, we need to say, okay, if you have your edge places here in your space, what is the value, what is the relation between, and maybe I can make it a little bit more graphic with colors. So the function of a point like that is in R, and the function of a point like that is in R. And the question is, how do these relate, right? What is how the values of the vertex point and the edge point relate? And you might want to say, well, if I have, let me label things again, 1, 2, 3, 4, 5, and maybe let's just say A, B, C, D, just for labels. You might want to say, okay, so perhaps f of 1 can be related, oops, I forgot. 1, 2, 3, So 1 minus f3, for example, right? If these are numbers, I can subtract them. This quantity should probably be somehow related to f of a, right? So
Why the difference, not the sum?
Well, plus minus times, who knows? I mean, it's really quite flexible. I mean, it was just to motivate, right? Like if you're thinking in terms of if I'm traveling from 1 to 3 and I want to see a continuous path, if I begin at f1 value and I end up at f3 value, maybe you want to say that fa is the average of f1 of f3, right? Like, why not? But then if you are in considering the values of f3, f5 and f6, then what is the value in the edge, right? Is the three-way average? It's not so obvious how even if you have absolute certainty that you're chosen your real numbers and you're certain to do this, it's going to depend a lot on what you want to do with it eventually to decide one way or the other, right? So that's one leg of the problem. I don't want to get too deep. We can discuss. I really want to have time to get everyone's ideas and everyone's opinions. I just want to get to where the problems I see are. So that's one problem. How exactly you distribute the values of your function on your edge places and all your possible places. Further, I would say, do you even need values everywhere? It might be that you want to assign intervals of values or sets of values for intermediary places because you want to say something like, that's what an edge is in some sense, that whatever value was in 3, 5, and 6, the edge is saying that that's in between all of them. So maybe you want something like a region of numerical values that include all of them, something like that. Anyway, that's the general question of how you assign the values to places. The question of which is which numbers to choose, right? So the question here is, is it R? Is it Q? Is it Z? I don't know. Is it C? Is it...
Can I ask a question at this point?
Yeah.
Related to this. So why do we need to apply something like numbers to the situation? Why can we not derive the concept of numbers from this graph?
I like your thinking a lot. I like very much your thinking. So I was kind of trying to get someone to say that, so you're absolutely perfect. So that's exactly how I'm thinking about this. I think throwing numbers from an external sort of, as I said, that's why I emphasize that this thing, there's this platonic real line floating here. To me, feels artificial to the spirit of infrageometry, right? So, and because there's this ambiguity of what field of numbers to use, just compounds this artificiality or this sort of unnaturalness of that choice. So I love your suggestion that we should somehow not impose numbers, but somehow discover numbers in our structure. And that's exactly where I was going. My intuition right now is that if we are to choose a field, and by the way, by field I mean, so a field F, basically means that you have addition, multiplication, 1, 0, and distributivity. So times plus equals times plus times. Right. So this is. Sorry.
You can divide, right?
Okay. Sure. Yes. Technically, I mean, addition and multiplication they have inverses, right? So, I mean, that's implied here, with inverse, except for 0 and so on. But this is based. Yeah. Go on.
By numbers, James, did you mean like discrete numbers like Z, or did you mean like elements?
I
Do you
meant,
want to
thinking
divide
of-
Z and stuff?
yeah.
Yeah,
So
I mean, like I was thinking of it in terms of just like maybe like Zeno accent or something where you have like a point and then you have a successor and then the successor of the successor. And you can kind of like go, if you choose any one trivial vertex, you can define like numbers from there.
yes.
Okay.
No, but so that's a very good thought. But also, when I say number, in this context, I meant a field, and that's why I was explaining what I meant by a field, right? So a field, I think of this algebraic entity, in which I can do addition, I can do multiplication. I have something like a 0, something like a 1, and there's this distributivity property, right? Invertibility, I don't even care that much about the invertibility of multiplication, because you could have a ring and it's still fine, or an integral domain or whatever. It's that's not so important. What's important to me is the fact that.
Hold on, there's a problem with the sound.
Can you hear me?
There's a comment in the chat about sound.
Um,
Is there a problem with the sound? Maybe someone could comment in the chat.
can you hear me well?
I'm just gonna listen to the YouTube. Give me a second.
Maybe the live stream problem. We can hear you.
I think it's good. I think it
It's
might be
good,
the
it's
user.
good.
Yeah, I think it's good. Yeah. Thanks, Fadi, for keeping us back. Yeah. So anyway, I was just going to formulate this thought, James, that choosing a field seems all choices of fields to me feel quite artificial, except
Even a boolean.
except maybe for that. That's exactly what I was going to say. Except maybe for the last one I have here, F2, right? That's the one that I might consider if I were to follow this narrative where a function is just an assignment of field values that's why I wanted to call them numbers, because we're saying vector field and scalar field, and like it's going to get tricky. So if you don't mind, when I say number, I hope everyone understands I'm referring to a field algebraically, right, with these axioms. So something that, but I think it's important to call it a number as well, because we might want to stretch what we mean by number, right? Exactly in the direction that you're saying, James. So we might want something more minimalistic, heavy technology, so to speak. I mean, it's as heavy as, having defined negatives, which for infrageometry might be too far of like definitions, right? So let's keep it very minimalistic. Now, what would be a good way to do this, right? One simple possibility is that in the same way that your hypergraphs are essentially Boolean functions already, right? If you give me and let me make this point. You give me a set of vertices, and you say you're gonna consider arities up to n, or up to 1,000 or whatever. You're gonna have some finite model, so your maximum arity is going to be whatever. Then, given the set of vertices, you automatically have the set of all possible subsets of those vertices up to that arity, right? Given that your cardinality might be lower than, smaller than that. So, in other words, given a collection of vertices, you can always define the complete graph and the complete hypergraph in any arity, right? That's what I'm saying. So, an actual simple undirected hypergraph, all it is a Boolean function over the total complete hypergraph, right? Where it assigns a 0 when there's no edge there, and when it assigns 1 when there's an edge there, right? So in some sense, the fact that our data structure, the spatial graph data structure, which is, as we are saying, reminding everyone, simple undirected hypergraph, the fact that we're choosing that to be our spatial graph kind of points to Boolean functions as Boolean values as the natural choice, because in some sense our model already speaks that language, because it can be formulated in that language. So the proposal here will be as simple as saying places are assigned. Each function is an assignment of Boolean values to each place, right? And so that's that's good enough. I mean, again, that fits this definition. So it fits the fact that you automatically have an algebra of functions. You can add functions. You can multiply functions. You can, subtract functions. You can do all these things. There's the function 1. There's the function 0. Like you automatically get a ring of functions on your hypergraph, just by virtue of the fact that you have point-wise operations, and you just completely run with the traditional definition of the commutative algebra of functions. You get that out of the box just for free in this setting. Now the question is, does that make sense? Does that purchase anything useful for us down the line, making that function definition? I'm not fully convinced. I don't know. I think it's part of the discussion. So
does it matter if there's multiple options? Shouldn't we be exploring all of them?
It is good to have several options. I think what I wanted to discuss in this call here, and this is, by the way, me officially sort of opening the discussion part of the call, is exactly how to explore the set of options. Because the set of options seems too large for me, in the sense that by saying booleans, f2 here answers one half of the question, which is which field of numbers, but it doesn't really answer how. Like it doesn't give me a lot of structure. Now it's true that the Boolean field is very small. I mean, it's as small as it gets, basically.
Can I suggest one alternative? Maybe
okay.
For half.
Go for it.
Right. For example, your like restriction to for hypergraphs to be simple, maybe not necessary.
Not necessary.
Right? So
no.
Imagine you can have multi-edges back,
sure.
And now just those multi-edges count as multiplicity. So that's the natural case for having integers on the edges, right?
Correct.
So now you assign your integers to the blue place, and then because your edges can be also directed, right? Now you can also assign naturally some value to the vertices themselves by some kind of sum all the directed edges minus all the ingoing edges minus outgoing, something like that, like the flow. Right?
Okay, but so what you're proposing is something that, given a hypergraph structure, defines a function, right? Somehow.
Yeah.
So is then your proposal that functions should be hypergraphs, or what? What is?
Well, multiplicity just weights. Just natural way to give weights to the hypergraph, but yeah.
Yeah, I mean that's the same thing, right? Like let's say you assign a value to each element, which is a place, which is an edge to each place. Sorry, which is an element of the vertex set or an element of the edge set, right? So it's essentially the same, right?
So it is a hypergraph, but you kind of distinguishing how by multiplicities of hyperedges, all the fields. I just distinguished, so the same structure of the hypergraph if you simplify it, but all the different fields are just different multiplicities on different edges.
I understand, and my only concern, I mean not concern, it's more like the picture of the hypergraph being sort of base space and having different possible functions defined on the same base space, like what you have in, the real line is unique, and you have as many functions as you want to consider, whatever, the interval 1, 0, or whatever, right? Like in calculus, in conventional real analysis. So how, like that's kind of the point here. Like if we have a hypergraph which is sort of fixed, and that's our unit interval or our manifold or whatever, we want to have a family of all possible functions on that same space without touching what the space is in some sense, right? At least that's the intuition that I have by default coming from geometry, but I don't know if you're suggesting something.
So here we're also not touching the structure of the hypergraph, right? We're just adding more multiplicities on each edge. So the structure is kind of the same. It's just
Okay, I think I see your point. Okay. You're saying that if we were to, for example, think of the spatial hypergraph as the simple graph, right?
Yeah.
And then multiplicity is what defines the function. That's what you're saying, basically, right?
Yeah, basically.
Okay. Yes. Okay, let me make a note of that. That I understand. Functions as multiplicities. That's interesting. Okay. I see only one ambiguity there, which is the fact that vertex, its multiplicity is obvious. Vertex multiplicity, we go back to this theme that's already sort of a running joke almost, that we might want unary edges to represent the multiplicity of a vertex, and that's kind of this.
No, I was suggesting to compute some kind of flow through the vertex, right? Because you have edges, they kind of point to the vertex or from the vertex, so you can subtract all the ingoing from the outgoing or other way around to get the number in the vertex.
But I would disagree that given a hypergraph with multiplicity, I would disagree that that defines a distribution of values, of integer values on the vertices.
It defines on the edges, but you can infer the.
But how? But not uniquely. Not uniquely,
Hmm?
right? Not uniquely.
Well, maybe you can come up with some clever scheme to get it unique, but yeah.
But it's highly non-canonical, right? That's my concern. It's like very non. I like the idea of I like the idea that functions can be multiplicity, but maybe I just expanding your suggestion to say, let's bring unary edges to be first-class citizens. They are always forgotten. If you take your definition verbatim, as you said, but you just remember that you might have unary edges, right?
Well, it's fine. It's like you think of each edge as a source of some liquid or whatever. It's already blue here. Imagine it like flows through the graph, right? So,
sure.
And whatever the amount of flow through each vertex is, that's the value.
But that's basically just the degree in each vertex, right? It's like the added degree.
Kind of. It just depends. So if you have if there's a ternary edge, right?
Mm-hmm. Like here. Yeah.
Like there you have it. Like it's not just adding a single point of flow. It's like it's maybe 1/3 of that flow defined on D. So your D is your ternary edge, right?
Yeah.
If it has some multiplicity, it defines how many potential flow it can distribute in different directions. So the number 3 only gets like maybe 1/3 of that.
Something like that, you mean, right?
Yeah.
Yeah. No, I mean that looks very natural and obvious. I'm not questioning this. I mean, I agree, but my point is that I worry about once you give a distribution of edges, two criticisms. One, unary edges have no role, which is always not a problem, but maybe something to consider in your perspective, because if they have a role, they are then just adding some extra numbers everywhere, and in your definition. And the second concern, there is more actual concern, is the fact that there is no real sense on which by changing let me put it this way: you cannot get arbitrary distributions of values on vertices, on vertex places, just by adding multiplicities, right? In the sense that because they are going to be constrained, right? So F3 and F4, sorry. I think that's the best way I can put my apologies. My tablet is getting warm and it's getting.
You can always with unary edges, you can basically assign any weight to a vertex if you want to. So it's kind of
that's my point. Yeah, that's my point exactly. But so this is what I'm trying to say, right? If you define functions on vertices exactly as you're saying, no reference to unary edges, or even with reference to unary edges, but the point is the values at a F3 at 3 at 4 are always going to be related by some proportion or something, right? Like this B half, this is explicit that F3 is always going to be F4 plus something. This is always true, but what I'm trying to say is that
that's just the nature of your graph. If you don't want them to be related, then there shouldn't be any edge called B between 3 and 4.
Okay, I see your point actually. Okay, I see your point because sorry. you're answering the actual question of the full question of how to distribute the values. Okay, I understand. I see. Okay. I am fully getting your proposal now. I think that's a very good idea. I think, yeah. And I think we can use unary edges just to represent, yeah, like some concentrated quantity, right? In some sense, it's like some concentrated space. That makes sense, right? It's, if you think about the analogy, it's kind of weird to think about a unary edge, right? It's like the space in between the thing itself. It's like it's a bit psychedelic to think, but no, but I like your suggestion a lot. So function values as multiplicity, and then yeah, that basically summarizes it. So unary edges give vertex wise functions. Would you be happy with that? Like,
Yeah. Fine.
okay, so okay, so then we are technically choosing n as our so it's not a field, but it's fine. It's we can add things together. Udi?
Yeah, so I was just commenting on Nick's suggestion and I had good questions about it. Over here, you're saying that the function value of a vertex is technically completely determined by the function values on the edges.
Yeah.
Places.
Yeah, that's right.
Yeah, assuming that the values everywhere are 1. Yeah.
Sorry?
Assuming that the values everywhere are 1.
What values?
No, but didn't you say that this is saying that the values of the functions at the vertices are determined at the values at the edges?
Yeah. And values on the edges determined by multiplicity.
Exactly, and values at the edges are, which is what I meant by, if you think of the actual multi-hypergraph, it's like the value of the function is 1 in all edge places, and
You can think of like a complete hypergraph.
Yeah.
Hold on. You can think of
you're saying
like
that given a
complete hypergraph, like with all possible hyper edges,
Yeah.
and you just, if you want to remove some hypergraph to make a different hypergraph, you just assign this multiplicity of 0, right? So it's just
yeah.
so you have a hypergraph, then you can determine like the function values.
Yeah, just by counting multiplicity. Yeah. So we're basically saying that it's almost like, I like this a lot because this is very interesting, because in the same way that we I mean, the way that vector fields, tangent vectors are defined in differential geometry, they make reference. I mean, I need to, sooner or later this diagram needs to be somewhere. So I'll just I'll just mention it here. So the fundamental theorem of calculus is formulated on this kind of setting, where a curve is a map from R to a manifold, and maybe your manifold has some holes or whatever, and your functions are maps from your manifold to R. So this thing here is a curve, this thing here is a function, and what happens in between is that there's a tangent vector over there at TPM, and that thing is defining some directional derivative of a function, right? So it's in this picture, right? The reason I'm mentioning this picture here is that to define curves, you have this external, quote unquote, artificial real line, which is basically the time parameter to define your path. And in functions, you have this external real line to define your values of evaluation, right? Like the results of evaluating your function. And so when you basically close the oops, you close the diagram over here, sorry, what you get in this composition is just a conventional function, like in high school, right? Like this thing is just R to R, no, it's like your homework from high school. So, and that's how.
Sorry.
Yeah.
Just a quick question. Is it correct to think of it as a time though, because it's just purely spatial hypergraph?
As a what, sorry?
Is it correct to think of it as a time parameter, even though it's just a purely spatial hypergraph?
Wait. You mean
parameter of the curve, right? It's not time because it's not like space-time.
No. It is. Yeah. It's just a flow parameter. So, but in this is the smooth geometry picture, right?
Mm-hmm. Yeah.
So this is smooth. And in this context, I call it time because it's just a flow parameter, which you could say sort of observer-dependent time or something like that, like in that sense. But my point here is, I just wanted to close what the thought. The thought is, given that this is the case, that is kind of symmetric, right? That there's kind of a symmetry of either you come from R and land into M, into your space, or you come from M and you land into R. So first case is a curve, second case is a function. This is how differential geometry is built. Like this diagram is the first thing you encounter in the first few pages when you start differential geometry, and you get back to it in many different ways. Like you define tangent space in 5 different ways, you prove they're isomorphic, blah blah, all that stuff. So my point, all I'm saying is I really like Nick's proposal and what we're coming up with here, because if we are saying that functions are essentially just multiplicity, and I note how at the very beginning I said simple because I kind of wanted to remove that from the picture. So if we don't make that simplification and we allow for unary edges, suddenly the information of what would look like a function is automatically there, right? Because multiplicity is naturally additive, and we now that our task for, I guess, next week, or homework for next time, is let's try to start to make sense of constructions in calculus with this definition, right? So maybe we can use the final few minutes to sketch those and to have a because obviously
before we move forward.
No, for sure. Yeah. I don't want to. Yeah. Go ahead, Uti. Yeah.
No, I was just very confused over here. Like, I always thought, like, if you're trying to define functions on a graph, you could have multiple. Right? And over here on a graph, it's like another structure encoding the same information as a graph.
So yes, the thing is, you might want to think. So okay, so mathematically speaking, this is like saying, if I know all the functions that can exist in my space, that's the same as knowing the space, right? It's the classic duality, like algebra geometry duality, right? So the analog of that result here, I would say, intuitively at least, is the fact that if you give me all the possible hypergraphs that can exist on a given simple all the possible multi-hypergraphs that can exist on a given simple graph, on a given simple hypergraph, right? Or maybe even on a given set of vertices. I don't care. Like maybe the total one is
you can determine the simple graph.
Yeah, so I think you can always project down to the simple graph. Like you give me a hypergraph, you can project to the simple one, and you can say that the quotient of all those, all the possible multigraphs that preserve the topology, so to speak, up to multiplicity, that's kind of the pure space. That's why I was saying, think of a simple undirected, and that's the spatial information. Right?
Maybe you can just restrict to the vertices themselves, right? Without any edges, right? You just given a list of pure vertices without any edges between them. You add an edge, that means just you're adding like one multiplicity.
Yeah.
So it's like a whole set of functions that they can also have can contain value 0, right? So
yeah, I mean Uti's question is important because he's pointing at something important here, which was more or less my pushback when you were trying to explain this suggestion, which I like, but we still have to make sense of this because we are running on this. We might be careful not to run too much with the analogy of classical differential geometry, and we might want to drop, and that this might be the point where we say, well, we drop the exact analogy here and we take it from here. But what Udi is referring to is the fact that, as I said, generically you have a space on which you can define a space of functions, right? You have or a set of functions. Here we're saying we can construct such an analogy with our setup, but it requires a little bit of fine tuning in the way of, for example, saying, if we are saying that a simple, if we take seriously the kind of narrative that I've built over the live stream today and that we've been working on, the fact that some diagram like that, some kind of spatial graph, some simple undirected hypergraph is a candidate for space. If we all agree on that conceptually, then you might say, how does it, multiplicity doesn't really make sense in terms of betweenness information. If you think about actual space, right? When you think about two points, and all you know is whether there is a space or not between them, meaning can you connect them spatially or not? That's a Boolean valued thing, right? It's not there are 7 ways in which you can connect this, just as a primitive statement of only is there a space at all between them or not, right? So I really want you to visualize like space, like things floating in outer space, or like a landscape on Earth or whatever. Like if you say there is a triangle between these 3 objects, you're saying there is one triangle between these 3 objects, right? Like you're saying there's like an area enclosed by the convex polygon between these 3 objects. You're not saying there's like 3 parallel universes in which there are 3 triangles I can construct. There's only one, right? So and this is very different from the statement of there are this many ways to get from one to the other, or there is this many ways to embed a sphere that connects them two with the others. And these are questions that might have multiplicity-like answers, but the statement, the pure basal statement of betweenness, this idea of is there at all some space between these things or not, that's a Boolean, right? And so maybe we can incorporate function-like information, like Nick suggested, simply by throwing sort of redundant betweenness information on top of things, right? By saying, well, if you just multi-edge over here, which is the same thing as to say that we weight over integers our hypergraphs, right? Then we can just use the formalism of hypergraph rewriting, because again, remember, the goal here is that we try to reproduce and replicate the functionings of differential geometry without actually doing differential geometry. We don't want to just, find a trick where we shortcut and then we take a limit and we have a manifold and then we just work with manifolds. Here, the goal is to try and have a formalism that is essentially replacing, giving a surrogate system instead of that takes hypergraphs as the main objects and doesn't require you to go to commutative algebra and do Lie algebras and so on. Ideally, we would want to prove some results like, oh look, when you assume these kinds of things about your hypergraphs, you don't even have to take a limit. You actually have proper Lie algebras and so on, right? That's kind of the goal here. Do you understand, Uti? Is that a bit clear?
Oh, yeah. Yeah, I think it's very, since it's discrete, like I don't think we even need to go there.
We don't.
We can.
That's right. Yeah. That's right. So we don't, but we need to somehow, what I would say, not conceptually, but thematically, we want to be analogous, right? Like in the sense that,
right. Yeah.
We want, and maybe let me put on the screen the last few bits before this runs over 3 hours almost. Because I mean we've been online for 2 hours now, but so I'm happy to go for a bit longer. But this is sort of pushing the limits of what a sort of effective live stream can be. So I love the suggestion, and it connects very nicely with the general philosophy that we were discussing previously for the candidate for the answer to this question in red on the screen. Which was, okay, kind of no-brainer. We are at the Wolfram Institute. We know how to do hypergraph rewriting, so maybe the answer to everything should be hypergraph rewriting. But I don't want to mean I don't mean to say that in a sort of derogatory manner to when we actually do that, when we say, okay, let's try rewriting here. But what I mean is that it is, in my opinion, very naturally justified that you would want to replace your calculus on manifolds with what Stephen will call, and maybe the branding should make sound something like infracalculus on these hypergraphs, right? So, I don't know what Stephen had in mind when he defined this term. He said, oh, infracalculus is what we do with this. I'm sure, I don't know, Nick, if you remember when he came up with the term in some live stream in the physics project at some point.
What term?
Infracalculus.
Yeah.
So was it what was he thinking exactly about when he phrased that? Do you remember?
Yeah. I don't know.
Yeah.
No.
I think it was something like, I mean, I can imagine because what he explained, but it was basically if we are saying that you get these models of space-time discretely by generating rules with hypergraph rewriting, then everything that you normally do on a manifold we should be able to replicate here somehow. And so that thing that you do on a manifold you call tensor calculus, and this should be something like calculus, but this infracalculus.
I think there's any rewriting were in his mind that time. Just in general, discrete system, we should be able to describe them.
Exactly.
Do some calculus.
Exactly. So to me, taking the rewriting philosophy to its ultimate consequences means that we, in this context, we should consider rewriting as the natural choice. And I can argue for this. And the one best example I can think of is exactly the algebra of vector fields, right? In this context. So let me not take too long to do this because it's been a long live stream already. But how to motivate it? Okay, so in affine geometry, so in your traditional flat spaces, Euclidean spaces, one way you can define the addition of vectors is as so. Okay, sorry. Let me just tell you a very brief story. If you're in a affine space, this is affine, meaning it's some flat Euclidean space. There's no preferred orientation or coordinates or anything. If I give you 2 points like that, tell you this is P and this is Q, and I draw a vector between them, and I call it V, you can say, well, what if I had another pair of points over here? I'm going to call M and N. They define some other vector W. You can ask, okay, if I'm in P, I travel to Q with V. What happens if I travel from Q with W, right? So you can put W over here, which you all know is some Euclidean geometry operation. You're saying, take the parallel line, blah, 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 take it here, go the same distance, all that stuff. So the point is that you end up on a new point. Let's call this Q prime or something, right? That thing is now, again, has some displacement vector from here, which we can call U, for example. So this is U, right? So this operation that basically you start at a point, you consider another point, then you consider some other pair of points with the displacement, and abstractly, just using the rules of Euclidean geometry, you flow from P to Q and then to Q, from Q to Q prime. That process is what we abstract mathematically, and we say that U as a vector is the sum of V plus W. Right? That's how it's algebraically. That's how that's encapsulated, right? So if so we know that this is an abelian group, blah blah blah. It has all the algebra attached to it and so on. The vector field, the addition in vector fields in geometry here, what I had here on the screen, this addition over here is essentially that kind of addition, right? It's inherited from that. It's not exactly that, obviously, because it's kind of pointwise and everywhere, smoothly, whatever. But it's essentially inherited from this kind of addition. So if I'm going to think of a vector field, in some cartoon, I'm going to have some discrete graph with some points. And now I'm not even distinguishing between edges or places or whatever, but I'm just going to have some, vectors like that. This is whatever, right? If I'm going to have something like that, something that looks like that, then the idea would be, okay, a vector field is one such thing, right? One segment of such things. A y, whatever, it's another graph like that. It might be a different set of arrows if the lag allows. Wow, that's like 3 seconds to draw the whole thing. So this might be a y, right? And you might visualize them on the same graph like I did here in the same plane and whatnot. The idea is, if addition was this pattern, where you had v, one flow in one direction, w, one flow in another direction, and v plus w was the flow that was combined from the two, it's only natural that you would think of the combined flows in your graph. Now, combined flows is sort of a bit of a misguided direction, because this is actually happening infinitesimally at every point of each tangent space. That's what addition of vectors is. It's infinitesimal at that point. So what it's really doing, it's doing it in a tangent space, sorry, in a model affine space, like this square here, and then shrinking it infinitesimally to be as arbitrarily close to the point that you're looking at, and taking the result as the resulting vector, right? So, which is not exactly the same, but the spirit is definitely equivalent. And so for this, I will turn to my notebook once and for the final time. I will just escape here. I'll share the screen again over here. And so what I call infracalculus would be, you would implement the patterns that you normally want to spot and you want to implement as explicit rewriting rules. So, for example, the addition of vectors happens to be, we all know the parallelogram rule, right? It's I drew only one corner of the parallelogram in my drawing there, but basically you could have done the other way and you would have gone into the same place. So v plus w is the same as w plus v. So basically, one way you could encode this is that whenever you see a pattern of edges, and here I'm being a little bit sloppy with if I mean vertex or edge, that's going to be subtle, but the sort of idea of the gist of it is that if you want to do something that is going to evoke addition, then what you do is you take the parallelogram diagram and you implement it as a rewriting rule, right? And that's it. And there you have it. You have a rewriting rule that is A in the same direction, parallel, B in the same direction, parallel, right? And that's how you define it. Like other operations are much clearer, right? Like opposite, so taking minus of a vector is literally just flipping the orientation of a directed edge, right? This was by construction. We are not doing anything like completely crazy here. But now something also interesting is the fact that vectors can be composed. So addition is very strong because it requires that, in the continuous setting, conceptually, you need to be at the same point, meaning you need to use the fact that you're infinitesimally close to the point to define addition, right? So that's why it's kind of a stronger condition that you need, a parallelogram of edges to compose into addition. Here, composition is less restrictive because all they're saying is like first flow with one vector and then flow with the other vector. You're not assuming anything about that you have to be parallel or anything like that, right? So this is going to be subtle. This is going to be quite detailed in practice because we might want to define the sort of the path groupoid of the graph and so on, and we might want to make this rewrite rules apply only to the paths and not to the actual edges, and like this might be a little bit more sophisticated than just this simplistic approach. But the general theme is that we don't need anything other than rewriting rules on hypergraphs, which in some sense is not really abandoning the land of hypergraphs, because it's all it's saying is doing pattern matching with the data structures themselves, to encode something that is very similar to addition, reversal, and so on. And now, of course, the goal here would be to, I think Nick and I drew some, maybe, no, it wasn't in the other notebook. But basically the expectation would be that you could try to recover some algebraic results. So, for example, if you define addition in this way, and you define opposite in this way, is it true that a plus minus a is always the zero vector, or something like that, right? The zero vector being maybe like the loop vector, the loop assignment to all the presets, things like that, right? You can start to make those questions, and the answers is never never going to look like, oh yeah, for all vector fields you would have that always you can define an opposite that always composes with a direct to form zero. That's never going to be a statement like that, but it's going to be something like, whenever you have a region of your hypergraph where this is defined, you're going to have a multi-way system of rule application that is going to work in a way that is deterministic, that we can sort of compactify and say, you know, like this we sort of block consider as there was a plus minus cancellation of vector fields in that region. So on the one hand, we lose totality in the sense that everything is going to be partially defined by default, just by construction. But then we also lose the notion of complete algebraic structures. So you're not going to have something that is a set of well-defined objects that get operated into well-defined objects. You're going to have a big bag of things, and they're going to evolve and react. And your vector fields are going to change a little, and you're going to change a little bit there, and so on. And so the expectation is that we can, via the analysis of those behaviors, discrete rewriting behaviors, we might be able to mirror what the algebra does in the continuous setting. And so there might be several strategies to like make the final claim of something like, if we take a limit and give some constraints to what the hypergraphs can look like, can we recover explicit differential geometry? My hunch is that absolutely yes, because if you imagine that these hypergraphs are sort of like triangulations of manifolds, I am pretty sure, at least intuitively, it feels like these constructions are going to recover the simplicial constructions that people do in differential geometry with the right tweaks and sort of turns. And there might be other strategies, like saying we have partial algebraic structures that recover things partially and things like that. Yeah, Udi.
This is really nice. I really like the rewrite over here. But the thing, I have a question. So
Yeah.
in here, you're formalizing or like you're trying to define addition of vectors and composition of vector fields as just very simplistic diagrams, which are essentially like left-hand side to right-hand side, which is a rewrite. So addition is not the rewrite rule itself, but it's like a like the representation of it. But you're saying that if we start from a simplicial complex or something, and if you have a bunch of rewrite rules that essentially, you know, denote addition or subtraction or those things, you're basically saying that the reason why the simplicial complex will limit the manifold is because now you can like all the results are there, like the algebra is closed. Is that what you're saying?
Yeah.
And that's why you're recovering these?
Yes, that's right. So that's exactly right. So that's the kind of game that you start to play is instead of it's actually, I mean, the analogy is actually quite strong with the continuous case, by the way, because if you ever wondered, this might be an anecdote that's a little bit tangential, but if you ever wondered why people work over infinitely differentiable manifolds, you might wonder, why infinitely differentiable, right? I understand it's a simplifying assumption, but I mean, infinity is not necessarily simplifying, right? Like, why do you have to assume something that seems so strong as you can differentiate as many times as you like, and you will always get a continuous function as a result? That's what it means to be infinitely differentiable. You might be wondering, why make that choice when, all of the laws of physics are formulating up to 2 or 3 derivatives? And, it's like, why do we need those assumptions? Why aren't those assumptions unreasonable? They might be unreasonable for physical reasons, who knows, but they're very preferred because assuming infinite differentiability is what allows you to have such a clear-cut algebraic picture, right? So
Precisely. Because you can,
yeah, so infinite differentiability is what, for example, buys you the isomorphism of derivations of your ring of functions and your sections of the tangent bundle. So these two things, they can be defined in any regime of differentiability, but only when you have infinite differentiability for general topological manifolds. Only then those two things are isomorphic. And just speaking of derivations of functions turns out to be the same as speaking of vector fields, right? And
Yes.
and a lot of differential geometry is built on this equivalences, right? And this algebra geometry relation. And that relation just happens to be super elegant and super exploitable when smoothness is assumed. Smoothness meaning infinite differentiability. So in this context, what I would imagine is that we might need to similarly demand from our rewrite rules some kind of behavior that is analogous to this infinite differentiability or something like that, where if you make that assumption, then your rewrite systems are going to have some very nice properties that you can start to make some global equivalences and saying, anytime you have two vector fields, this operation is always well defined, because you're going to have a multi-way system, but it's always going to be confluent to a single final state. And that final state is a well-defined output of vector field X, vector field Y, output whatever, X plus Y, right? And so, and that's kind of the gist of it, right? Like, knowing that the way in which, if you have something like a vector field or something like a function scalar field, a curve, a submanifold, so on, in classical differential geometry, the way to operate with those there was to make them into some algebra, right? Like you try to pull them away from the pure geometry or the pure topology, you put them in some algebraic terms, and then you compute with the algebra, right? And this could mean just literally putting in coordinates and expressing everything like complicated coordinate expressions and polynomial expressions and coordinates and whatnot. Or it could be some clever use of Lie algebras and some representation theory, whatever. It doesn't matter how. But you put it into some algebraic terms, you compute there, and that tells you something about the geometry. So the spirit here is absolutely analogous in the sense that we are going to come from something that is like there, like some spatial hypergraph is sitting there. It might be very large, it might be complicated, whatever. And our computational probes to that thing are going to be rewrite rules. Right, we are going to measure things like, okay, apply this rewrite rule over here, see what happens. It's very, very sort of cellular automata like, very, very much thematically with what Stephen has always been thinking about and so on. And I honestly think, I wish that I could not, that I had to like somehow shield for Stephen and say, oh yeah, everything's cellular automata here. But I honestly think that this is the best way that you can approach trying to come up with an honest, minimalistic sort of definition of geometry without geometry to speak, geometry without real numbers, geometry without so on. When you have computational devices at your disposal, I think this is honestly the best way to do it. I mean, I'm not saying one way, I'm saying a large class of different possibilities here, but this general approach of relying on rewriting as the main way in which you infuse life into your static structures, right?
Can I see
I think so. It's like
after this one? So you have opposite rule, addition rule. What are the other ones that you put on this conception?
Composition. So this would be just composition of flows. But this is very confusing to me because these two things are quite separate in differential geometry. To flow with a vector field, you need to integrate it. To add two vector fields, this is an infinitesimal operation, so you don't need to integrate it in some sense. It's like it works because it is defined arbitrarily close to every point on your manifold. So it might well be the case that in infrageometry, these two things are now on equal footing. It might very well be the case that, what addition means and what composition means is just two flavors of the same thing, which is that two vector fields interact in some sense of parallel flow somehow, right? It might be. But yeah, the picture here is a bit diffused.
So this is pretty like elegant because essentially what you're trying to say, or like what we are trying to say, is that we're starting with different graphs, spatial hypergraphs, and then if we have some constraints on the spatial hypergraph, or like we definitely will have some constraints on the hypergraph rewriting. Like a lot of them might limit to the same simplicial complex, and the idea is that you can have the the space of possible spaces that are defined by spatial hypergraphs will be much greater than the spaces of continuous things. And let's say, I mean, just visualizing, I can think about it like if you have a line, like if you have edges like it goes like this, then if you try to apply these rewrite rules, you're gonna end up like an infinite line. And like over there, you can't define addition because you don't have parallelograms. But that's analogous to saying that you only have one basis vector, like um, because adding like a vector with itself is like scaling it, so that doesn't really make sense. So, I mean, immediately there are like correspondences like in terms of dimension. Yeah, I think.
Yeah, exactly. Yeah, that's right. And we might want to like imagine are the infrageometric models recovering finite geometry models? That's why we wanted to call it something different, because there's a lot of research done in simplicial geometry, finite area geometry,
Yeah.
all these kinds of the fact that I mean simplicial complexes were invented for this purpose, right? They were literally invented to reduce computations that would otherwise take infinite area operations, like taking an integral over a continuous space,
Okay.
reduce them to a combinatorial object, right? Like you could compute, the Betty numbers of the sphere or something just by expressing in your adjacency matrix, all the entries, and you just do linear algebra with that, and you compute the actual Betty numbers.
This is like even one step below.
Say it again.
So this is like even one step below like the
That's right.
visual geometry.
That's right. That's the understanding, and that's precisely why we like the infra branding, where we try to say we are somehow below the usual level of operation of conventional mathematics, right? I mean, it's
Sorry about that. I just realized I can annotate the screen.
yes. No
That's
worries.
pretty cool.
No worries.
Just a quick question on this.
Yes, please.
So almost just to summarize, we're trying to specifically at this point find the connection to differential geometry, because there's a lot of interesting concepts here which we can take in multiple directions. Like for example, how using this rewriting system that you're just presenting here, can you think about higher arities? Like these look like binary operations. How would you look for like ternary and more operations? But is that a different thing to tackle at a different stage? Like we're trying to zoom in on differential geometry right now.
Well, I guess the point is, first we want to see how far we can get with an analogy. That we know the theory of differential geometry quite well. We know that it's basically the foundation of most, if not all, of modern physics, right? And so the expectation here is almost like it's sort of like an orthogonal angle of attack from Stevens' approach, which was, okay, let's just throw something in the melting pot. Let's see, let's bring the temperature up, meaning let's run very long computations and see what comes out, right? And sure, there were very interesting results, and there's a lot more to be done there with the causality structure and observer theory and all that stuff that we will pursue. But this is a different approach. This is saying, okay, assuming that something can come out of pure just rewriting of hypergraphs and discrete combinatorial structures, can we somehow smell the trace of promise here? I don't know how to express it. Like,
What does the geometry look like? In other words, like,
yeah.
What's interesting with these hypergraphs is that the way they visualize makes them appear like there's some kind of geometric structure. There's some like 3D representation, but that's just a representation of the underlying computation. There's no way to formalize that those things are specific locations or directions or anything like this. So perhaps this approach allows you to take a hypergraph that's been rewritten and actually construct a geometric representation of the calculation, something like that. Is that possible?
That's one direction. Yeah, that's actually what I was going to go. Thanks for bringing that up, because I wanted to comment on what are the possible strategies or directions in which we would claim that this has been successful or not, right? Before I answer that, just as a point for future reference, now that Nick has suggested that effectively multiplicity of the hypergraph or multiplicity functions in some sense are going to be our functions, I imagine that this rewrite rule is going to be super important to understand like directional derivatives and things like that, because this is basically the transport rewrite rule, right? If you have some edge count here, this rewrite rule, takes you to the other place. And by the way, you could imagine that you have your hypergraph with multiplicities, and you take those on the vertices only as that many unary edges, right? So you can. What I'm saying is, you can basically measure numbers by multiplicities of unaries. Like that's a pretty natural thing to do. So yeah, I think this rewrite rule is going to be very, very natural there. And something that I know about this rewrite rule already. In fact, I might just so people don't think I'm just claiming things unjustifiably. So there is, I think it's here. Actually no.
You also might want to build a rewrite rule for like filling in like a hole. Like have a triangle rewrites to like a
so
reasonality.
I think you're not seeing the second notebook because I'm sharing the notebook itself. But I will share very briefly this other notebook that you guys have seen several times, just for the audience. If I go to, action, you would see that this is exactly the rule. I mean, it's not showing correctly. It's not rendering there. Let's see if this is fixed now. Nope. Yep. Okay, label is a bit all over the place, but that's the rule, right? You have two vertices, one edge, one directed edge, and you have a unary edge A on this end, and then what the rewrite rule does is basically pulls the edge A into the other vertex, and you call that the action of X on A, right? That's what this notation is. So this label is for this edge, this value there. It's not, I don't know why it's showing that way. And what's interesting is that if you consider this rule together with the arrow composition rule, which is the usual sort of morphism composition that everyone's familiar with, right? Like arrow into arrow, right? The interesting thing is, you know that this thing is associative just by the property of this rewrite system, the arrow rewrite system. Now, if you take the action and you combine the two rules, so you combine the arrow action composition, which is this, and the arrow composition, which is the one the two arrows compose above, and you draw a minimalistic diagram on this, what you get is the property of associative actions. So you get exactly the property of what we call flows in differential geometry. You get associative actions are essentially, this idea that you can do one and then the other. So that's why you would call it a flow. Right? I'm being very broad strokes here, and this is not trying to prove anything, but thematically, it seems that there's going to be something there. Right? Like it seems that clearly, if we are thinking that our functions, values at every vertex can be represented by just the multiplicity of edges, unary edges on those vertices, then these kind of rewrite rules are going to encapsulate quite well the idea of flow, right? Which is exactly what you want to represent when you say a vector acts on a function, meaning how much is it flowing in the direction of that. We're going to have direct rewrite rule based probes to measure those kinds of phenomena. Because the way to think about this is you will have your vertices populated with integer number of unary edges, like these little a's, right? And each time that this rewrite rule applies, it's basically applying one edge at a time, right? So it would do the pattern matching, so it would send one packet, and then it would apply stochastically somewhere else, and then maybe it applies there again, and so it sends another package, and so on, right? That would be the kind of system that emerges instead of saying, object acts on object gets object, that will be the algebraic traditional mathematical sense. This will be much more sort of organic in some sense, much more sort of stochastic, multi-way, as you want to call it, right? Anyway, just as an aside, that I think things are quite convergent here in terms of how we're thinking of these things.
This is pretty good.
Yeah.
But I think the sad part is that all the stuff that we did on like derivations, like weighted derivations, is not going to be useful because this is like a completely different idea.
I don't think.
I actually like this
Yeah.
idea.
No, this is great. No, I agree, but I think the weighted derivations direction should, like, that's something that we need to account for, because it's a construction that, the weighted derivation story is something that we can explicitly recover in our setup. So in a way, we're going to have it as the template for what to compare it to, as well as Lie algebras and so on, because the fact that you can imagine defining finite difference operators, these things are well defined on our graphs, right? It's not something that you have to construct from our graphs. They're just well defined on our graphs, and so if you know that these finite difference operators generate these algebras, these weighted Lie algebras, all that stuff. If we find those weighted Lie algebras somehow with these rewrite rules, then that's great. That's a good check. It's some kind of a reality check, right? If we know that they are naturally in a graphic structure, sitting there, if we rediscover them or express them in terms of rewriting.
I don't know if you remember, the vector composition rule was actually like corresponded to like an actual composite. Like, remember the operator that we found for, like, if I compose two weighted derivations, I get another one.
Yeah.
Like, apparently we said that it was an open question, and then we found our operation in terms of functions.
Yes.
Like, that corresponded very neatly to just composition of vectors, if you remember.
Yes.
So yeah, but I don't know. I think it's going to be extremely challenging.
Yeah, it's going to be difficult, but all these questions will be quite, pie in the sky kind of questions when we actually try to solve them, because they are not like well posed, concise mathematical questions. We don't have like something, is this isomorphic to that, or does this set contain these other subsets? They are not formulated in those terms. They are formulated in much broader conceptual ways. But I think the goal here is to, this is a very exploratory, it's a very sort of Wolfram Institute-like project. It's a very exploratory project where we don't know exactly where we're going, in the sense that we know that there's the promise that hypergraphs encode all this combinatorial information in a way that is analogous to how differential geometry and topology encodes spatial information. And it's our job we're not solving a problem. It's not that we have a problem, we're going to solve it, although one might find problems in physics that might have a better angle of attack with our approach. But we're more saying, can we, given this assumption that hypergraphs are this very powerful, minimalistic, computationally enabled data structures, given this, can we find the analog of what doing differential geometry and algebra on these things would be? And that's what the project is about. So that's why I like that Nick suggested multiplicity, which is something that's just intrinsic to hypergraphs, and that we are going into the root of the rewrite rules, because that's kind of what the natural language of this context, So
I think we should just stick with. I think since there are so many choices of definitions we can make, I think we can stick with one and then see where it goes. I think it's
exactly. Yeah.
Yeah.
That's very good.
Very, very
Yeah.
open. Unfortunately, we'll have to run in some time, but it was a nice discussion.
No, this was amazing. Thanks very much for taking the time, and best of luck with your exams.
Yeah.
Oh, thank you so much.
So I guess we can make some final comments or thoughts, but I think I've said everything I wanted to say for sure, and got a lot in return.
Yeah, maybe just to continue the thought that I had earlier with regards to applying or extracting geometry per se out of hypergraphs and hypergraph rewriting, it could be quite interesting, because that you could construct a three-dimensional visualization from that would be true to, you know,
yeah.
it'll be true to like an actual space. I don't know if like what your thoughts are with that. I mean, it would be difficult. Like, it wouldn't be an actual object, but you could envision that you can actually create a ball from raw computation.
Okay, so two clarification points. First is that when we say geometry, we really mean abstract geometry in some sense. So we're not necessarily sort of calling back to 3D space or 2D space geometry. The second thing is there are essentially two classes of, as far as I can see, two categories of strategies to recover geometry from this discrete setting. One is much more similar to what, or much closer to what you are suggesting, that we take the information that's there and somehow infer a geometry from it, which could be something like, you know, if all you have are unary, binary, and ternary edges, which is kind of our working setup, just for simplicity and computational times and so on, then you might be thinking, okay, I'm going to call this the simplicial analogy, or the simplicial mindset. The simplicial means that you're going to think of those things as cells in a simplicial set, meaning, right, Udi, good to see you. So you're going to think of them as cells, and so meaning a pairwise edge is going to be like a line, a three-way edge is a little triangle, is going to be like an area, and so on. You're going to think of those as like literal analogies there. That's what the simplicial mindset means. That's what I mean by that. So if you do that, then indeed the kinds of hypergraphs that we're looking at, they will be basically piecewise 1 and 2 dimensional manifolds, right? So they would be more or less nicely represented in 3D, and so you're absolutely right. That's the direction that we can take. The other direction, and more generally, I mean, if you increase the arity of the edges, and you even don't assume that because the simplicial picture really forces you to consider a lot of things that we are not considering, because we're doing this undirected, sort of very sort of parsimonious hypergraphs. But even if you're not doing that, you can sort of infer geometry from hypergraphs. You know, and this is a kind of a problem in, you know, like topological data analysis and things like that, right? You can do sort of network analysis on your hypergraph and try to infer geometry, and try to think about it very explicit, like embedding properties. You know, like what is a good embedding for this thing? Can I fit this hypergraph on some manifold that is already existing in some higher dimensional space? Blah blah blah. All that story totally applies here. So that's another direction. Well, I would put them under the same category of sort of inferring a geometry, like an explicit literal geometry, out of the hypergraph data. But another category of strategies, which is the one that I had more in mind when working with Uti and all this idea of weighted derivations that came from this finite difference operators and whatnot, is the idea that if we know what differential geometry is mathematically in a very algebraic sense, so you could go all the way down to the fact that you have commutative algebras with Lie algebras, vector fields, blah, 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 all that stuff, or very broadly like topos theory and, you know, all these sort of more categorical representation of things. If we could somehow argue that the definitions that we've made fit perfectly in some exact setting, or maybe naturally extended setting of previously existing algebraic descriptions of geometry, then I would say that's a strong claim that we have recovered geometry in that sense. So in a way, you never really see geometry. This is really, you know, when I did my thesis, I think I put at some point in my thesis I wrote a reference to this phrase. You know, differential geometry is basically what is it? All for geometry, but without geometry, right? Like that's kind of the motto of differential geometry. Because I didn't even touch a coordinate chart in my entire thesis, and I was claiming to be doing differential geometry all along, right? So it was all algebraic constructions and local simplifications and patching over charts and things like that, but I never actually had to do geometry in some traditional sense. Anyway, so this would be like a proper all for geometry but without geometry, like it's really just completely removing the geometry from the picture, where you say let's do something with discrete hypergraph combinatorial computational structures. Let's try to map that into some categorical setting, some abstract nonsense. And if that abstract nonsense was mapping onto some geometry, maybe, then we say, well done, guys, we did it, right? So this is like geometry without geometry without geometry. It's like two layers of not being geometry. So in that direction, I think I am, it's exciting on the one hand because it's very open-ended and we have a lot of ground to cover, and there's a lot of potential for discovery because this is very new. I honestly think that we are the first people ever in history to be trying to do this, which is, I'm not trying to say we are like super important or anything, but it is just a fair claim. Like no one has tried to just recover differential geometry or an analog of differential geometry with rewrite rules on hypergraphs. I think this is just a fact of novelty. But I think I am but the flip side of that privilege, or that sort of being early, is that you don't really know where you're going, right? Like when you're an explorer and you don't have a map, it's exciting because you're the first person to get to any place, but you don't really know where you're going, right? So you might have a promise of like, oh, I might find gold in the next valley or something. That's kind of what we're doing here, but we don't have a direction we don't have a destination. Let's say we have a direction, but we don't have a destination. That's kind of that's how I see it. So we might want to be very tactical.
Just to extend that analogy, it seems like this isn't the first time a new land has been explored and a map has been had to be filled out. In other words, like when people explored new fields previously, it was a similar situation. So there's the promise of like what can happen when you complete a map of a new area, and we're just trying to recreate that in a new space. It's like these islands of mathematics and geometry and that sort of stuff. And like many islands have been explored before, and there's a new island that we're now traversing. And the direction is that, okay, let's try to figure out all the things that all the previous islands have discovered, and do those things exist here or not? I think that's the way to maybe think about it.
Absolutely, and not only mathematical islands in the usual sense, but as we are normally claiming here at the Institute, we are pushing the envelope a little bit on what it means to do mathematics even, right? Like in a sense that it would be inconceivable. In some sense, I almost feel guilty to be in the position that we are when we come up with these definitions, like what Nick suggested, and this idea of like maybe we can do addition of vectors with rewriting and so on. I feel a bit almost guilty for like all my fellow mathematicians that came before me in history, because this will be not a reasonable definition, and someone will like throw me away from a maths department a few years ago because, you say, sure, you say you rewrite things, but then what? Like, are you going to go rewriting with your hands every time that you have to rewrite? And now, because we have computers and we can represent everything computationally in some small examples, so we can do actual phenomenology of these things. Obviously, the place of proof is absolutely relevant, right? Like we want to prove things as well, like formally, as much as we can. But many of these things are going to be much more ugly than conventional mathematical elegance and conventional human mathematics, right? So,
like, would proof by computation make sense here? In other words, the elegance of it and the ability for you to synthesize stuff into a way that you can present it on a chalkboard wouldn't apply if the proof is by computation and the machine crunches the numbers and gets you the results that make sense. You can just carry on from there.
Yeah. So it's not only that the computer does the proof for you. It might be that you are not sure at first that you have proof-like statements to make, right? Like in the sense that that's what experimental mathematics means, right? It's not all of experimental mathematics necessarily is devoid of the possibility of proof. Absolutely, you want many times to have like definite proofs, and there are many. But there are many situations where, we're initially not assuming anything about these hypergraphs, right? We're just saying, we're saying that they are whatever undirected, but that's just like, saying whatever. And you're not assuming any regularity properties or anything. You're just making definitions that look minimalistic, but that don't really tell you what they are going to do in the end. So the kind of mentality that we are taking, at least the one I'm taking, is the mentality that one would have with conventional algebra, with abstract algebra. Right? You sit down and you say, okay, what do I have? Set, operation, property, law, whatever. That's it. So once I have these are the rules of the game. I can just run wild with this. So algebras are this sort of meat and bone rewriting machines, right? And just this, they're doing some in paper, some in their heads, but effectively they are just rewriting with all these algebraic rules, right? So I think I am an algebraist by practice. I think I'm a geometer by designation and an algebraist by practice, because effectively that's how all my mathematical life has been like. I had some rules, I put them on the blackboard, and I said, okay, where can I go with these symbolic rules, with the allowed statements, the allowed expressions that I have. So here we are doing something very similar in some conceptual sense, but instead of saying that our rules are capturing something that is completely abstract from reality or from the phenomena that we want to study, at least in the context of the physics project or infrageometry, we're saying no, we are actually capturing more or less a direct analogy with space, meaning landmarks, betweenness information, path information, and so on, and we're making that computationally alive, right? We're saying you have rewrite rules that apply, you have composition of paths that apply, and so on. And a lot of people will tell us, oh, but you have all the theory of path groupoids and all that stuff. Nobody cares. These are sheaves on, you can just do all that. Sure, and this will be great to do, but that doesn't really answer any of the questions of what if you have a hypergraph that has whatever 10,000 edges and 100,000 vertices or something, that potentially is a model for some physics phenomenon, like some black hole dynamics or something, right? What if that's what you have? You don't have a manifold. You don't have, an algebra. You don't have a category or, some object with some unique morphisms in a category. You have literally that, because it happens that, maybe your numerical relativity runs better on that, or might be that the physics project tells you that this is important for this or that reason. That might be your starting point, that this is or you're doing some kind of network analysis, and your network information is that your data is just in that form, right? So what do you do with that? That's your primitive information, right? So right now we're in the position where we can play the symbolic computation game with these kinds of data structures, not just abstracting from them and then playing a symbolic game. We can be more sort of first order with them, and that's why I say I feel almost guilty, because these definitions of sort of vector composition and so on. When I teach differential geometry, and when I was in the university, like teaching my students in undergrad mathematics about differential geometry and about the vector calculus, these were literally the diagrams I would use to explain the concepts, like the kinds of things that we are using as sort of our rewrite rules and so on. These are literally the diagrams that you would use to explain what an integral curve is and so on. So it feels almost, it's kind of uncanny that this is the theory that we are developing. We are encoding those as our formal building blocks for a sophisticated, advanced mathematical theory, math computational. I don't know what to call it, but this kind of hybrid that we're going for here. And yeah, it has the advantage that it is immediately intuitive to work with, and you don't have to throw all these definitions and technical definitions about topology and so on, which is absolutely important to do when you have to do them. But here is just another way of doing things. This is a bit of a change of gears.
It's a truly bottom-up approach, basically.
That's right. Much more bottom-up. That's right.
That's awesome.
Nick, do you have any thoughts? I thought I caught you at one.
No, well, maybe I have, but I don't want to prolong this any longer.
Okay, but can you at least just put a pin on it or something? But just mention it.
Closing remarks.
It's not a remark. I had some technical suggestions and all that.
I just don't want to miss the opportunity of noting them down. So I mean, we can just.
I will notice them. I will mention them quickly, just like from all this picture we were describing, we were missing like one of the things like duals of vectors and angles, right? And inner product.
Perfect. Fantastic. Yep.
It would be nice to discuss them, like maybe for the next time.
Next time, let's go dual. Let's go, yeah, because that's the. It should come quite naturally. Just as a comment, it should come quite naturally in the sense that, once you have functions and once you have vectors, you should have everything, right? Like, it should be a natural construction how you do dual, because dual is just sort of like the tangent of a function, right? The differential of a function is the covector, and you know, it should all come together nicely. So, but yeah, very well mentioned. Yeah.
Okay, cool. Well, I think that was a nice little marathon session to get us all caught up on the latest state of the art developments in infrageometry, and yeah, let's pick it up with some cadence. I think there's some new ground to explore here, and the quicker we can cover as much space as possible, the quicker we can find that gold that might be lying on the other side of the island.
Yeah, absolutely. Well, it's a privilege as usual, gentlemen. See you next week.
Yeah.
Goodbye, everyone in
Bye.
chat.